Hello students, in this video I am going to discuss about the sequence detector, the same 101 sequence detector using Murray machine model. In the last two videos I have just introduced what is meant by a sequence detector in the first video and the types of sequence detector, namely your melee, namely your overlapping and non-overlapping. For melee machine I just introduced, and then I have discussed about the melee machine model sequence detector for both the types, namely overlapping and non-overlapping. And in today's discussion I am going to discuss about the same 101 sequence detector but by using Murray machine. You know what is your Murray machine? It is also a sequence detector and it's a finite state machine. Your output here depends only on the present state, not on the input. It is not dependent on the input. It is not dependent on the input. It depends, output depends only on the present state, and you know what is your basic Murray machine model and how it looks like, and we have discussed for the serial adder also. Okay, so in the diagram we will in the video we will draw the state diagram and then go ahead with the state table, K map and implementation. So keep in mind, since your Murray machine depends only on the present state and it is not dependent on the input. Okay, so in the state diagram your output is written within your state itself because output is dependent on your present state. Hence output is written within your state itself in the state diagram. Okay, so here 101 sequence detector. In the Murray machine model, how we have taken, if it is 3 number of bits if we need to detect, we have taken 3 number of states and we have started designing it and we have implemented also. But here in Murray machine we have to take, if n is the number of bits, we have to take n plus 1 as a state. Okay, 4 states we are having, like that we have to take and we have to start the designing. Okay, so let me first go ahead with the overlapping model. Okay, I will draw the state diagram itself directly, then you will be familiar. Okay. So what I said, we are going to detect 3 number of bits, namely 1, 0, 1. So n is the number of bits, that is equal to 3. So the number of states will be n plus 1. So it will be 4 states. So we have 4 states here. Okay. So let the states be S0, S1, S2 and S3. Okay, and the state assignments for each states will be 0, 0, 0, 1, 1, 0 and 1, 1. Okay, 1, 0 and 1, 1. So this is the state assignment and the number of states. So as I said, so we have 4 states, namely S0, S1, S2 and S3. Okay. And keep in mind, you are going to represent the output also in the state itself, Okay. So the correct sequence is 101. The correct sequence is 101. So when it is in the initial state, namely your reset state, initial state, and when you receive 1, it will go to the next state. When you receive 1, you will go to the next state. Output you will be representing within the state itself, Okay, your output is 0, and you will move to the next state and your output is 0, Okay, and then come to your next sequence. Your next correct sequence is 0. Okay, 1, 0 and then again 1. Okay, so 1, when you are in state S1, upon reset, when you receive 1, you will go to S1. When you receive 0, you will go to S2. When you receive 1 again, you will go to S3. Okay, you will go to S3, making your output to be 1. For all the other cases, your outputs are 0. So output is indicated within your states itself, Okay, keep that in mind. Okay, so S0 is the initial state. Okay, initial state, and its output is, its associated output is 0. Initial state, output is 0, because we are not at diagonalize the bit sequence. Okay, that is why I have given 0. Okay, when we are receiving S1, your output will be 0. Each in Murray model, keep in mind, output will be indicated along with its states, because output is dependent on the present state. Output is dependent on the present state. So S1, if you receive 1, S1, it moves to the state S1, but your output is 0. And again, when you receive the next correct sequence 0, and your output, you move to the state S2, and your output is 0. And similarly, when you move to the next state S3 by receiving the input 1, your output also 1, because you have received the correct bit pattern 1, 0 and 1. Okay, 1, 0 and 1. Okay, now, so for each state, only one bit we have diagnosed. The correct sequence only we have taken the root, but the incorrect sequence also we need to discuss. So now, what is the incorrect sequence? So now, when we are in state S0, when we receive 1, you will go to the next state. But what happens when we receive 0? When we receive 0, you will be in the same state only. By your output is also 0. And again, come to your S1. When you receive 0, you go to the next state. But when we receive 1, okay, when we receive 1, you will stay in the same state. You will stay in the same state. Okay. It is like first we are receiving 1, again we are receiving 1. You are getting me? So the first sequence we have discussed is 1, 0, 1 sequence. And the next sequence is when we receive 0, 0, 1. How will be your path? And the next sequence is 1, 1. If you have 1, from S0 you move to S1. And again, if you receive 1, you will be in the same state only. You will be in the same state only. And then go ahead with your S2. Okay. Now, after this you have received 0. After this you have received 0. Okay. So first you are receiving 1. You are in state S0. You receive 1. Go to state S1. And then you receive again 1. You remain in the same state S1. And then receive 0. Go to state S2. Okay. And now, okay, if you receive 1 in state S2, when you are in state S2, you go to S3. But if you receive 0 again, okay, if you receive 0 again, what will be that? See, in overlapping sequence, what is said to be overlapping sequence? When you consider the previous bit, when you consider the last bit of the previous sequence to be the first bit of the next sequence, then it is said to be the overlapping model. See here, 3 things are over. 3 things is already over. 3 bits already you have diagnosed. Okay. So the last bit of the first sequence is 0. When you consider this as the first bit of the next sequence, okay, that is said to be overlapping model. Okay, that is said to be overlapping model. Okay. So when you are in state S2, now you are in state S2 after receiving 1, 1, 0. Okay. Now you are receiving 0 again. When we receive 0, okay, when we receive 0, where you need to go? Again you need to start fresh, because we don't know what it will appear in future. Okay. But this is a overlapping sequence. Already it is 0. So when you receive 0, so you need to move. You are considering this previous bit 0 also. So now here, from here S2, you have to move with state S0. Okay, because already you have received 0. Okay, already you have received 0. Okay, and now when you receive 1, after this, when we receive 1, okay, after this, the bit pattern may be different. So I am talking about when we receive 1, when we are in state S2, we move to S3. When we receive 0, we have to start fresh again. Okay. So this is like 1, 1, 0, 0. Okay. 1, 1, 0, 0. Okay. So let me discuss about the next pattern. So now we are in S3 because we have received 1 now. Okay, now let me assume that it is 1 0 1. Let me receive 1 0 1. When we receive 1 0 1, it will from S0 to S1, S1 to S2, S2 to S3. Now we are in S3 again. S3 will take two values, right? 0 and 1. 0 and 1 it will take. Now we are in state S3. So now we have again for state S3, again we may receive two inputs, one may be 0 and another may be 1. If we receive 1, okay, we need to consider already that is that we have received we had 1, okay, because it's an overlapping sequence. So 1 1 we need to check like that. Next 3 bits you need to check, meaning already 1 is there. So already if it is 1 is there, where you have to go from S3, you need to go to S1 because already we have checked this one. The next bit input bit is 1. Okay. So when we receive 1, we need to go to S1. In the same way, when we receive 0, okay, okay, when we receive 0, 1 0 1 0. So now it will be 1 0 is received, like 1 0 is received. So 1 0 is received. Correct sequence 1 0 is received. Okay. So you need to go to S2. Okay, you need to go to S2. This is your state diagram of the overlapping Murray-Mission model. Okay, overlapping Murray-Mission model. So let me discuss the state diagram of the non-overlapping Murray-Mission also. Okay, non-overlapping Murray-Mission also. Non-overlapping Murray-Mission, we won't be considering the last bit of the previous sequence. Okay, the previous sequence or the previous sequence bit pattern. Coming to your non-overlapping. Again, you are going to deduct only 101 sequence. You have 3 bits. So, number of state here in Murray is n plus 1, 4 states. So, 4 states S0, S1, S2 and S3. Okay. So, S0, S1, S2, S3. The correct sequence, initial state is this. Okay. Output 0. And the correct sequence is 1 0 1. So this is the correct sequence, and your output, when you receive 1, your output is 0. When you receive 0, your output is 0. Only when you receive the correct sequence 1 0 1, your output will be 1. Murray-Mission model output depends on the present state, so output will be mentioned within your state. So now again, S0, since it has received 0, it will move here. If it receives 1, it will move to the next state. If it receives 0, it will retain in the same state. And again in S1, when you receive 0, you go to the next state. When we receive 1, you will retain in the same state. Okay, right. So now come to S2. When you receive 1, you go to S3. But here, when you receive 0, okay, when you receive 0, it's like 1 0 0. Okay, when you receive 0, again you need to start fresh. Okay, you need to start fresh. So this is by receiving your 0. So when you receive 1, you need to go to the next state. Now you have 1 and the 0. Now the difference here between the non-overlapping and overlapping lies here. Okay. So now the sequence that we are going to deduct is 1 0 1 1 0 1 1. If you have 1 0 1 1 1 0 1, you are in state S3 now. Now you are going to receive 1. When we receive 1, earlier when you receive 1, You moved in non-overlapping. When you receive 1, you go to this state. You moved to S1. But now, okay, now, again what you are receiving? Again you are receiving 1. Again you are receiving 1. So again when you receive 1, where will you go? You will go to the same state here. Again you will go to the same state. But see here, when you receive 0, that takes a difference. When you have 1 0 1 0, for example, 1 0 1 is the correct sequence. Now you are with 0. Now you are receiving 0. 0 means you need to go to the initial state itself. That is the difference here. This is the only difference between the overlapping and the non-overlapping. Okay, again you are starting fresh. Again, this bit, you are not considering 1 previously. Again, you are starting fresh from the beginning when you receive 0. Okay. And when we receive 1, we are considering that already we have received 1, we are in state S1 and then we will move on. Is it okay? This is the difference between overlapping and non-overlapping. Okay guys, this is the state diagram of the overlapping Murray-Machine model for detecting the sequence 101. The state diagram, just now I have discussed how to draw the state diagram. So for the correct sequence 101, you will be moving ahead with the next subsequent states, and also you will be having 4 states, namely S0, S1, S2 and S3. You will be having 4 states. Okay. So this is the correct. When you are getting your correct input, you will be having transition the next state. And when you receive 101 only, and after moving to S3, you will be making your output to be 1. Okay, keep this in mind. So when your current state is 0 0, when your input is 0, when your current state is 0 0, this is the state assignment. State assignment for S0, S1, S2, S3 is 0 0 0 1 1 0 1 1. So when you are receiving 0 0 and your input is 0, you will be in the same state itself. Your output is also 0. Okay, so you will be in the same state, your output is also 0. And again, when you are in a state S1, that is 0 1, and when your input is 0, you will be moving to S2, but your output is 0. So your output is 0. And when you are in state 1 0, when you are in state 1 0, and your input is 0, you will be moving to S0, so 0 0, and again your output is 0. And when you are in 1 1, the state, okay, when your input is 0, 1 1, when your input is 0, and you move to S2, S2 is 1 0, and again your output is 0. Okay, output is 0. And now, when you are in 0 0, when you receive 1, when you are in 0 0, when you receive 1, you move to state S1, but your output is 0. Okay. And when you are in 0 1, when you receive 1, you will be in the same state 0 1, and your output is also 0. And when you are in 1 0, that is S2, when you receive 1, you move to S3. Okay, your input is 1, you will move to S3 and your output is 1. You are in 1 0, you are in 1 0. When you receive 1, 1 0, when you receive 1, you will move to next state 1 1. And what about your output? In Murray-Machine model, output is same as the present state. Present state is 1 0. 1 0, your output is 0. Okay. And present state is 1 0. So when you are in 1 1, when you receive 1, okay, your output is 1, and you move to state 0 1. Okay. And when you have your D flip-flop, when we have decided, I have decided to implement this by using D flip-flop. D flip-flop, your next state will be your input. Your QA will be DA and QB will be DB. So fill the same thing as like your DA and DB. 1 0 0 1 0. Guys, here I have committed one mistake. See, when you are in state 01, when you receive input 0, you will be moving to the next state, that is 10. So this is 10. Okay. So fill this up. 1 0, and QB plus and DB is same, all 0, the last 4 you will be having 1. Okay. So this is your state table, and with this you have to go ahead with your K-map for implementing your circuit. See, we need to focus on your expression for dA, dB and y. Okay. And keep in mind, in Moray model, your output depends only on the present state. It won't depend on the input. So for dA, dB alone, you will be having a 3 variable K-map, namely with variables x, qa and qb, and for y you will be having only 2 variables qa and qb. That we will see in the next slide. Okay guys, I already said this QA will be QA plus will be DA and QB plus will be DB. Okay, and output is nothing but the present state will be your output. Okay, whatever may be the present state, and in that what is there in the output, that will be your appear in your output. So in S0 will be 0. Only for your S3 condition you have 1. So S3 condition is 1 1. So when your present state is 1 1, for your input 1, you will be having your output to be 1. Okay. So for all other cases your output will be 0. Okay. When your state is when your present state is 1 1, when you receive input 1, your output will be 1. Your output will be 1. So let us go ahead with the K-map. So we need 3 K-maps for implementing your circuit 101 sequence detector, that too overlapping sequence detector. Okay. So we need 3 expressions, dA, dB and y expression. So we need 3 flip-flops. So 3 variable K-map we are going to draw, and let us fill up the dA column by seeing the dA column and dB column and y column. Okay. Okay guys, see, and I need to tell you one thing here, and what is that is, you for your dA and dB you will be using 3 variable map. Okay, for your dA and dB you will be using 3 variable map, whereas for the output here in Mealy model, okay, in Mealy model, what is your Murray model, I'm sorry, in Murray model your output depends only on the present state, it is not dependent on the input. So for deriving your expression for output, we will exclude the input, we are not going to include your x is the input, right, and the present state only it is considered, because the present state determines your output. So qa and qb will be your present state, so you will be having a 2 variable K-map here. For the rest 2, for deriving your expression dA and dB, you will be using a 3 variable map. Okay. So I have filled up here, and let us. So we are deriving for the overlapping model. We are designing for the overlapping model now, and I have filled up the table here. Okay, I have filled up the table here, dA, dB and y, and let us derive the expression. So this is this 2 I can combine, and this is separate only, and all the 4 we can combine here, and this is separate only. Okay, and keep in mind there is no don't care state here, because we have 4 states. Okay, in Murray model. So dA is equal to x bar, and this is QB plus x QA QB bar, and this is DB is equal to x only, and y is equal to y is QA QB. Okay, so implement this. Okay, implement this. How you are going to implement this? This is expression. So Moulay machine model, you have this. So again you will be giving your input is x, QA and QB is your present states. Okay, so this is your X bar, and QA, QB, QB, X into QA, QB bar plus, so we need an XOR plus QB into QP into X bar. This is QB, this is X bar. We need an OR. Okay, and this will be DA. And X is nothing but and your X is nothing but your DB. Okay, QU QB will be, this will be QA and QB. Okay, this is QB and this is QA. Multiply this, you will get Y. Okay, and feed this here. This is okay, D input, this is DB input, whereas this is your clock. Tie your clock and give your clock. DB is connected here and DA connected here. Okay, this is how you will be implementing your Murray machine model. Next we will go to the non-overlapping Murray machine. Okay, non-overlapping Murray machine. This is the state diagram of the non-overlapping Murray machine. Let me go ahead with this again. So with the state diagram, fill the state table. Okay, we know the state diagram already. Okay, so when you are in 0 0, when you are in 0 0, your input is 0. When you are in 0 0, when your input is 0, you will be remaining the same state and your output is also 0. Okay, and your output is also 0. So only when we are in 0 1, okay, you are in 0 1, when you are receiving you are in 0 1, when you are receiving 0, you will go to S2. S2 is 1 0. Likewise, fill this table along with your output. Output is same as a present state. Output is same as a present state. Present state is 0 1. So 0 1 is 0. Okay. Like this, fill the table fully. Okay, this is the state table. I have filled the state table. Except for when you are in state S3, when you are in state S3, only when you receive 1, you will make it, only when you receive 1, your output will be 1. Okay, if you receive 0, your output is not 0. So when you are in S1 1, only when you receive your input to be 1, your output to be 1. Okay, so for the rest all will be 0 only, for all the output will be 0. And the present state and the next state, you know how to fill this, and then I have filled it accordingly. And for the D flip flop, QA plus and QB plus will be equal to DA and DB. Okay, the same thing I have filled up here also. And then K map, and by looking at the table of DA, DB and the Y, and I have filled the K map. Keep in mind, for the output does not depend on the input, it depends only on the present state. Hence the K map should be drawn only with the present state alone. Okay, I have filled this up. So this is only one over here, and this I am going to take all the 4, and this is also an individually we will have this. So this is TA will be equal to X bar, QA bar and QB plus this is X into QA into QB bar. Okay. And dB is equal to X and Y is equal to QA into QB. Okay. And I have implemented by using two flip-flops. See here dB is equal to X. I have taken dB is equal to X. X directly and X bar into this one X bar into QA bar. From QA I have taken an inverter. So QA bar into and the third one is QB. Okay, that and the other and for this is X into QA into QB bar, this one, and both of them has to be XORed, and this is OR gate and I am giving it to DA, and Y is nothing but QA into QB. Y is nothing but directly I am taking it as QA and QB and I am multiplying and I am taking the output Y. This is the implementation for the Murray machine sequence detector for 101 sequence. Okay, with this I will stop today. Thank you.